All right. Today we are in day 2 of our ACT Prep Unit 3, which is elementary algebra topics, and today we're going to talk about exponents and radicals. So exponents, if I give you something like 5, I'll do their 2 to the 6th. Okay, they're 2 to the 6th. This whole thing is actually called a power. I know a lot of people call the exponent a power, but technically the whole thing is called a power. And a power has components. It has a base, which is the factor, and then it has the exponent, which shows you how many times the factor is repeated. So 2 to the 6 means 6 copies of 2 multiplied, not added, multiplied together, which would be 64. So a couple of exponent rules that you need to know. Anything to the 0 degree is 1. Anything. 16 caret 0 is 1. Type anything in the calculator to the 0 degree and it will give you 1. Anything to the 1st degree is itself. And know that everything has an exponent. If they don't write 1, it's a 1. When you multiply like bases, you keep the base and you add the exponents. So here, 7 to the 8th times 7 to the 5th, you keep the 7 and you add 8 plus 5 is 13. When you divide, you subtract exponents. So here, again, but the bases have to match. So if 7 to the 8th divided by 7 to the 5th would be 7 to the 3rd, because 8 minus 5 is 3. When you power a power, that's this one, I call this Santa Claus. If you use your imagination, that kind of looks like a house, right, with that X to the M inside. And N is Santa coming down the chimney. Well, when he comes down the chimney, presents get multiplied. So when you power, think of Santa Claus and multiply your presents. So if I have 5 squared to the 3rd, again, I power the power, that's going to be 5 to the 6th. And then last, you can't have negative exponents. So what you do is you move them to the other floor. I like the story of if you got a negative exponent, you got a negative attitude, you got a bad attitude, and nobody wants to be around bad attitudes and hate and nicky and nacky. So we say, get away from me. Right now, if I made this a fraction, it's over 1. So if I say, you got a bad attitude up here, I'm going to send you to the basement where you can adjust your attitude. So he goes down, his exponent turns positive, he's had an attitude adjustment, he's just down in the basement. Now this 1 didn't move up, it's just that when it moved down, there's a 1 left there. So an example, 5 to the negative 4th, you can't have a negative exponent. So you move him to the denominator, that turns the 4 positive, and your answer is 1 over 5 to the positive 4th. All right, so radicals, we have this 8 times, this would be read as 8 times the cube root of 7. Your parts of a radical, the number touching the radical, that's 8 times, that's called the coefficient. The number in the whole is called the index, and whatever's underneath is called the radicand. Okay, and what this says is there's a law that says you can convert from radical to rational exponent. All you do, the rule is, let's say that I have the nth root of x to the m. You can translate from this to what they call rational exponent form. In other words, you can get out of the radical. You take your radicand, and whatever is in the whole is going to be the denominator. Always, always, always. The index goes on the bottom. And then whatever power is there, or exponent is there, is your numerator. Okay? When you're told to simplify radicals, you are not done until there are no fractions in the radicand, all nth powers of whole numbers are removed, there are no radicals in the denominator, and the index is as low as possible. So a couple of rules you need to know. There's a law that says if you take the nth root of x times y, it's the same as the nth root of x times the nth root of y. An example is, let's say I had the nth root of 5 times 100. This law says I can write that, let's not do the nth root, the square root. This says that I can write that as the square root of 5 times the square root of 100. Well, the square root of 100 is 10, and the square root of 5 isn't real. I mean, it's real, but it's not rational. It goes on forever and ever and ever. So we would just leave that as the square root of 5. Okay, instead of, if you type this in the calculator, square root of 500, you're going to get a decimal, which isn't wrong, but they don't like decimals because that's an approximation of an answer where this is more exact. And this says that if you take the root of a quotient, you can split the top and the bottom. So if I take the square root of, let's say, 4 over 100, I can split it and say, well, the square root of 4 over the square root of 100. The square root of 4 is 2. The square root of 100 is 10. Reduces down to 1/5, and I'm done. Okay? All right. So, what to do? When you're told to simplify radicals, okay, like the square root, like this one we know, the square root of 16 is 4. If you know them, you know them. But the square root of 32, if you type it in the calculator, you're not going to get it. You're not wrong, but again, the ACT is going to give their answer in simplest radical form, not in decimal form. So they won't accept a decimal answer. So to simplify it, the trick is you're looking for perfect squares in there. Okay, perfect squares, like square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. These are perfects because they come out nice and pretty and whole. So what I'm looking for, are there any 4s in there? Are there any 9s in there? 16s, 25s? Okay, well, when the number's small, it's not that hard to figure out, but they're going to give you these huge numbers. So that's what these notes are for, okay? When you can't break it down easily or figure it out. If you will only divide by primes, and the reason you only want to divide by primes is because you're looking for these perfect squares. If I get 2 2s, that makes a 4. 2 3s makes a 9. 2 5s make 25. If I divide by things like 6, that's got a 2 and a 3 in it. I might be missing factors of 2 or factors of 3 that I can make into perfect 4s and 9s. So if you don't use anything but prime numbers, you won't miss any of your perfect squares in there. So what you do is you break it down by your primes. I always start with 2. If the number ends in an even number, you can divide by 2. So by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. So what I can do is, this can be rewritten, again, because I'm looking for square roots. I'm looking for 2 of the same thing. That would be 2 squared. That would be 2 squared, and then that would just be a 2. I don't want to bundle them in 3s. If this was a 3, I'd bundle them by 3s. If the index was a 4, I'd bundle them by 4s. But because my index is a 2, I'm bundling together as 2s. And 2 squared times 2 squared times 2 is 32. I still have 32 in there. I just broke it down, and now I can see the perfect squares and the not perfect squares. That law we just talked about said I can write this as the square root of 2 squared times the square root of 2 squared times the square root of 2. Well, now you can see your perfect squares. The square root of 2 squared, that's the square root of 4, which is 2. The square root of 2 squared is the square root of 4, which is 2. This one you can't get out because there's not 2 of them in there, so that has to stay in. So my final answer would be 2 times 2, which is 4, times the square root of 2. That is equivalent to that. Okay? 16, like I said, you should know that one. And don't do all this work if you don't have to. If you know it, you know it. But if you didn't know it, you could break it down. By 2 is 8. By 2 is 4. By 2 is 2. Bundle it. I can write that as 2 squared. That looks like 22. Times 2 squared. I can break that up. The square root of 2 squared times the square root of 2 squared. That's 2. That's 2. 2 times 2 is 4. Okay, the square root of 27, I'm going to break it down to its primes. I can't use 2 because it doesn't end in an even number. My next prime I try is 3. 27 divided by 3 is 9. By 3 is 3. I'm trying to bundle by 2's because my index is a square. I'm doing a square root. There's a bundle of 2, so I can rewrite this as the square root of 3 squared times 3. That I can split into the square root of 3 squared times the square root of 3. The square root of 3 squared is 3. This isn't perfect, so it stays in the radical, and my answer is 3 times the square root of 3. Okay, so let's break these down now. Alright, so if I take 224, where do I want to do this? I'll do it down here. And I break it down by its primes. It's even, so I'm going to start with 2, which goes 1, 1, 2. By 2 again goes 56. By 2 again goes 28. By 2 again goes 14. By 2 again goes 7. And again, remember your primes. And you don't have to remember very far. If you can't divide by 2, 3, 5, 7, 11, or 13, then what you're dealing with is probably prime itself. Alright, so then you're going to look at the index and see how you're bundling. Sorry, I picked the wrong color. I have purple. That's a 2, so I'm bundling by 2. So there's 2 2s, there's 2 2s. He doesn't have a partner, he doesn't have a partner. So he's not going to be perfect and he's not going to be perfect. So I can rewrite this as the square root of 2 squared times 2 squared times 2 times 7. Now, if you don't mind, I don't want to, well, maybe I should rewrite it for you. I'll rewrite them for a while, but again, eventually you don't want to spend a lot. You want to spend the least amount of time as possible. But I don't want to confuse anybody. We'll get a little lazy later. So this is the square root of 2 squared, which is 2. This would be the square root of 2 squared, which is 2. This has to stay in, and this doesn't have he's not perfect. So that makes the square root of 14 altogether. So you take your outies, 2 times 2 is 4. Your innies, square roots of 14. That would be my answer. 4 square roots of 14. Okay? Let's try another one. 250. I'll break it down by 2. Yes, you could start with the 5. Okay? But I'm OCD and I like to go things in order. When I go out of order, it makes me twitch. So 250 divided by 2 is 125. 2 isn't going to work anymore. I like to go in order, so I check 3. The trick for 3s is if you add up the digits and 3 goes into the sum, then 3 goes into the number. So 5 plus 2 is 7, plus 1 is 8. 3 won't go into 8, so I know 3 ain't going into 125. So now I'll go by my 5s. That would be 25. By 5 again would be 5. Once you hit a prime, then you got them all. Okay, check your index. I'm looking for pairs because the index is 2. I got a pair of 5s, and that's it. So I can rewrite this as the square root of 2 times the square root of 5 squared times the square root of 5. Okay? This is not perfect. This is perfect. That's 5. So my outie is a 5. Square roots of these two have to go back in as a product. 2 times 5 is 10. Okay? Alright, you try this one. Hit pause. Come back when you're ready. And hopefully you got 5 square roots of 13. If you didn't, let's look at why. So if I break it down, it ends in a 5, so I'm going to go with 5. That's going to be 65. Still ends in a 5, so 5 again would be 1 and 3. 13's prime, so I'm done. I'm looking for pairs. I got a pair of 5, so this is the square root of 5 squared times the square root of 13. That's 5, and that has to stay square root of 13. Okay? Alright, the calculator screen in figure P11 shows approximate values for 1 divided by the square root of 3 and the square root of 3 over 3. The two approximations are exactly the same, and that's not a coincidence. Okay? Some guy a long time ago, and I hope he's dead, because if he wasn't, I would find him and hurt him bad. Somebody, I don't know who, decided that this is ugly, that you can't leave radicals in the denominator. Okay? So they made up a law that says you can't leave radicals in the denominator. And they call that, to get rid of the radicals in the denominator, they call that rationalizing the denominator. And what you do, if your denominator is just a monomial, meaning it's just one term, as opposed to something like 1 over the square root of 3 plus 2. This would be a binomial on the bottom because it's made up of 2 terms being added together. Bi, 2. This is a monomial. There's one term. When it's a monomial on the bottom, you just multiply it by itself. The square root of 3 times the square root of 3 on the bottom is going to give me the square root of 9, which is just 3. So that will eliminate the radical on the bottom. Well, that's only legal if whatever you do to the bottom, you also do to the top. 1 times the square root of 3 is the square root of 3. And so that's, can you see that these are actually equivalent? It's been proven, but that's how they figured out that those were equivalent. Sorry, I forgot I animated this. Okay, this process is called rationalizing the denominator. Okay, this process involves rewriting a radical expression as an equivalent expression in which the denominator no longer contains any radicals. Excuse me. Again, that's called rationalizing the denominator. If the denominator consists of the square root of a natural number that is not a perfect square, multiply the numerator and the denominator by the smallest number that produces the square root of a perfect square in the denominator. Alright, so here they want me to rationalize the denominator. If they're all monomials, so I'm just going to multiply it by itself. Square root of 6 times the square root of 6. But if I do it to the bottom, I have to do it to the top. That becomes 15 square roots of 6 all over the square root of 36. Okay? And you're going, wait, you're not supposed to have a radical on the bottom. Well, I don't anymore because the square root of 36 is 6. Now, you got to reduce a little bit. You can't touch this inside number. Leave him alone. It's like he's in jail. You can't touch him. You touch him, you're going to get sucked into jail. So leave him alone. But if the two outside numbers can be reduced by the same number, then you're allowed to reduce. And I can reduce by a factor of 3. So, sorry, I'm trying to get my color here. If I divide by 3, 3 goes into 15 5 times, 3 goes into 6 2 times. My final simplified answer is 5 square roots of 6 all over 2. Okay? Alright, on C I have the square root of 18 on the bottom, which is not allowed. So to get rid of it, I'm going to multiply it by itself. But if I do it to the bottom, I have to do it to the top. On top, I'm going to have the square root of 18 times 5, which is 90. So I got the square root of 90 on top. And on the bottom, I don't know what 18 times 18 is, so I'm just going to write it as 18 squared. Okay. On bottom, that does it for me. The square root of 18 squared is just 18. So I've rationalized the denominator, but I have to simplify the numerator, which means I need to break down the 90. So I break down 90 by 2 is 45. 2 isn't going to work anymore. 3 will work. 15. 3 will work again. 5. Sorry. And I'm looking for pairs. So on top I have the square root of 2, the square root of 3 squared, and the square root of 5. The square root of 3 squared is 3. These two aren't perfect, so multiply and put them back. You got 3 square roots of 10. And I'm done unless I can reduce the outside numbers. Again, don't touch the 10. He's in jail. And I can reduce those by 3. 3 goes into 3 once. 3 goes into 18 6 times. So my simplified, rationalized answer is the square root of 10 over 6. And no, you can't reduce the 10 and the 6. Like I said, you can't touch the inside. Alright, on B, sorry, I guess I'm going out of order. To get rid of the square root of 8 on bottom, I'm going to multiply it by itself. But whatever I do to the bottom, I have to do to the top. So on top, I'm going to have the square root of 96 over the square root of 64. Which on bottom, square root of 64 is 8, so that's good. I rationalize, but I have to simplify the top. So I'm going to break down the 96. By 2 is 48. By 2 is 24. By 2 is 12. By 2 is 6. By 2 is 3. So we're looking for bundles of 2 because I'm a square root. There's a bundle, there's a bundle, and that's it. So I have the square root of 2 squared, the square root of 2 squared, the square root of 2, and the square root of 3. These are perfect. That's a 2 times a 2 times not perfect. Put them back together, and I get 4 square roots of 6. Okay, then always check your outies to see if I can reduce. I can reduce 4 and 8 by 4. 4 goes into 4 once, 4 goes into 8 twice, so my simplified rationalized answer is the square root of 6 over 2. On D, you have two choices. Usually I try and divide first and then take the root, but 100 divided by 9 is a decimal, so that doesn't work. So then I switch to that rule that says I can split them apart. The square root of 100 divided by 9 is the same thing as the square root of 100 over the square root of 9. The square root of 100 is 10, the square root of 9 is 3, and I'm done. Alright, you try one. Rationalize this denominator for me. Hit pause. Come back when you're ready. And hopefully you got 4. To get rid of that radical on the bottom, I'm going to multiply it by itself. So I'm going to multiply by the square root of 3, but if I do it to the bottom, I have to do it to the top. So on top is going to give me the square root of 21, and on bottom, that's going to give me the square root of 9, which is 3, which is rationalized. I'm good, but simplify the top. Well, 21, if I break it down by 3, is 7. There isn't 2 of anything, so there's nothing perfect in 21. It all stays under, and my answer is the square root of 21 over 3. Alright, definition of the principal nth root of a real number. The nth root of a equals b means that b to the n equals a. So the only thing that's different, guys, is now instead of bundling by 2, for this one we have to break it down and bundle by 3s. So if I take 24, break it down, by 2 is 12, by 2 is 6, by 2 is 3. Now to make a perfect, I'm not making a perfect square, I'm making a perfect cube. So it takes 3 of the same thing to make a perfect cube. Well, I got 3 2's. So I can rewrite this as the cube root of 2 cubed times the cube root of 3. The first one's perfect. Sorry. The cube root of 2 cubed is just 2. This isn't perfect, so it stays in. So my simplified answer is 2 times the cube root of 3. Okay, when you multiply, the only thing that has to match when you multiply are the indices. And that's plural for indexes. Okay, adding and subtracting is different. Everything has to look the same to add and subtract. But multiplying and dividing, the only thing that has to match is the indexes. And what I do is I'd say a 4th root times a 4th root is a 4th root of whatever their product is. 8 times 4 is 32. So then you break down 32. Now I'm going to be bundling in groups of 4. So if I break down 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. So I've got the 4, and I'm looking for bundles of 4. 1, 2, 3, 4 2's and 1 left over. So I have the 4th root of 2 to the 4th times the 4th root of 2. The first one's perfect because I bundled it up. The 4th root of 2 to the 4th is 2, and you can't simplify that, so it's 2 times the 4th root of 2. That would be my simplified answer. Okay, on C, you can try and divide first, but 81 divided by 16 is like 5.0625. That didn't help me, so we pull it apart. This is the same thing as the 4th root of 81 over the 4th root of 16. Now we break them down separately. So if I break down 81, 2 wasn't going to work, but 3 will. Goes 27 times. By 3 is 9. By 3 is 3. I'm looking for bundles of 4. I got it. Okay, that's going to be the 4th root of 3 to the 4th, which is just 3. So the top is 3. On bottom, break down the 16. By 2 is 8. By 2 is 4. By 2 is 2. Again, I need 4 to make it perfect, and I do. That's the 4th root of 2 to the 4th, which is just 2. So that reduces down to 3 over 2. Okay? Alright, so you try this one. Hit pause. Come back when you're ready. Alright, and you should get 5 cube roots of 2. So I have the cube root of 10 times the cube root of 250, which is the cube root of 250. Then I got to break that down. 250. I can divide by 2 is 125. 2 isn't going to work anymore. 3 doesn't work. By 5 is 25. By 5 is 5. I need 3 to make it perfect because my index is 3. I got 3 5's. So I got the cube root of 2 times the cube root of 5 cubed. Well, the cube root of 5 cubed is 5, times the cube root of 2 is 5 cube roots of 2. Okay? Alright, negative exponents. You can't evaluate these without getting rid of that negative. So all you do is you move it to the bottom, and then it becomes positive. And you're going, but what is that? Well, remember I told you, this can go back to radical form. Remember if I have x to the m over n, this is always going to be my index, the nth root of x to the n. So I can rewrite 64 to the 1/3, make a radical. 64 goes inside. The denominator is your index. The numerator is your exponent. Okay, and I got rid of the negative exponent and put it in radical form. So now all I have to do is simplify the cube root of 64, which means I'm going to break down 64. By 2 is 32. By 2 is 16. By 2 is 4, 8. By 2 is 4. By 2 is 2. I'm looking for bundles of 3 because my index is 3. There's 3 2's and there's 3 2's. So that's 1 over the cube root of 2 cubes times the cube root of 2 cubed. Well, those are now perfect. Cube root of 2 cubed is 2. Cube root of 2 cubed is 2. So that's 1 over 2 times 2, which is 4. And we're done. Okay, this one, get rid of the bad attitude, send them to the basement, turns as negative 3/4, positive 3/4. Go radical. This will be 1 over 81 goes inside. The denominator's the index. The numerator's the exponent. Okay, now, when you're doing something like this, you could order of operations would say you have to cube 81 first. But there's a law that says you can break this down, okay, and it can be the 4th root of 81 and then cube it. And that makes life a lot easier. You don't have to deal with these huge numbers. So let's break down 81. By 3 is 27. By 3 is 9. By 3 is 3. And I need 4 to make a perfect. And I got 4. So this would be 1 over the 4th root of 3 to the 4th. And then that's going to be cubed. Well, that's going to be 1 over the 4th root kills the 4th degree. So that leaves 3. But now I need to cube it, which gives me 1 over 27. Okay. All right, try this one. Hit pause. Come back when you're ready. Okay, it says, what is the sum of the factors of 3 to the 4th times 4 to the 3rd times 5 to the 2nd? Well, this says that there are 4 factors of 3. This says that there are 3 factors of 4. And this says that there are 2 factors of 5. Okay, so those are all my factors of that problem. They want me to do the sum, which means they want me to add all of those together. And if I add all those together, I get 34. Okay? Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got 9/20 times the square root of 5. Alright, on top we need to square that, which is going to be 9. On bottom, we need to break that down. So if I break down 80, by 2 is 40, by 2 is 20, by 2 is 10, by 2 is 5. I'm looking for bundles of 2 because my index is a 2. There's 2 2's, there's 2 2's. So I got the square root of 2 squared, the square root of 2 squared, and the square root of 5. Well, that's 2, and that's 2. So now I have 9 over 4 times the square root of 5. And you're going, well, that answer, so why wasn't that the answer? Well, you can't leave a radical in the denominator. So to get rid of it, I'm going to multiply by another square root of 5. But if I do it on the bottom, I have to do it on the top. On top, I'm going to have 9 square roots of 5. And on bottom, I'm going to have 4 times the square root of 25. But the square root of 25 is 5. Times 4 is 20. And that's the answer. It's just they wrote it like this. This is saying 9 divided by 20 times the square root of 5 over 1, which they can write like that. It's the same thing. Alright, so let's practice a little bit here. When you multiply and the bases are the same, you keep that and add the exponent. So that would be 7 to the 11. Okay, we're multiplying again, so I keep the 9. Negative 4 plus 7 would be 9 cubed. Okay, here the bases are not the same, so you cannot add their exponents. Plus, order of operations says I've got to take care of my exponents first, and these parentheses are there because I need to power the power. So this would be 2 to the third times 3 to the fourth. And you can't, I can't do that 6 to the 7th. You can't multiply the bases and add the exponents if the bases don't match. That's as far as I can go as far as my little exponent rules. Okay, 4, my bases are the same. That's going to be 3 to the 5 plus, oh my goodness, 5 plus a negative 5, which is going to be 3 to the 0. Again, these two, you can't add those exponents because the bases aren't the same. So, what do you do on those ones? Well, here, I typed in 7 to the 11th and got my answer. There, type in 9 cubed. Here, you just have to type it like this to compute it. I can't add those exponents because the bases don't match. So you just type 2 cubed times 3 to the 4th. Anything to the 0 degree is 1. But even if you typed that in, it'll give it to you. Again, this one, I can't add exponents because the bases aren't the same. So you just type 3 cubed times 9 squared, and you get 2187. Okay, the next row is dividing. When you divide, we subtract exponents. So this is going to be 5 to the top minus bottom. That's going to be 5 to the negative third. We can't leave negative exponents in our answer. So he's going to have to move down, which would be 1 over 5 to the positive 3. And then if you type that in, or you could just type 5 caret negative 3, you get 0.008. Math, enter. Again, if they don't give you a decimal answer, hit math, enter on your calculator, and that will turn it into 1 over 125. Okay, on this one, we can't subtract the exponents because the bases don't match. So if I just type it in, 4 squared divided by 2 to the 4th, I get 1. Okay, here the bases match, so we can subtract exponents. That's going to be 12 to the 5 minus a negative 5. Watch those signs. That double negative turns positive, and I end up with 12 to the 10, which if I type in, I get that big number, which they wrote in scientific notation. What that means is the decimal is really 10 places that way, so the number is huge. Alright, here the bases match, so we can subtract. We have 4 to the top minus bottom. Well, a half take away 1 is a negative 1/2. Bad attitude, that's going to move it to the bottom. That's going to make it positive. You should just, anytime you see a degree to the half, that's a square root. And that's going to be 1 over 2, which is going to be 0.5, or 1/2. Okay? Alright, here the bases match, so 6 to the 7 minus 2 would be 6 to the 5th, which is 7,776. Alright, so on these, okay, you can always try and see if they're perfect. This one you should know off the top of your head. You shouldn't have to do any math. Okay, 864, I have no idea. And if you type it in the calculator, you get a decimal. That means you can't use that answer. It's not wrong, but they don't want that estimated answer. So you're going to break it down. 864 ends in an even, so I'm going to divide by 2. Would be 4, 3, 2. Still ends in a 2. 2, 1, 6. Still ends in an even. By 2 again is 1, 0, 8. Still even. By 2 is 54. Still even. By 2 is 27. Not even anymore. The next prime that works is 3. So by 3 is 9. By 3 is 3. And I'm looking for bundles of 2 because my index is a 2. So I got 2 2s, 2 2s, 2 3s, and a leftover 2 and a leftover 3. So I can rewrite that as the square root of 2 squared, square root of 2 squared, square root of 2, square root of 3 squared, square root of 3. Pull out your perfects. Square root of 2 squared is 2. Square root of 2 squared is 2. Square root of 3 squared is 3. And these guys aren't perfect, so put them back together, and that would make a square root of 6. So I have 2 times 2 is 4, times 3 is 12, times the square root of 6 would be 12 square roots of 6. Okay, 13. They want the cube root of 56. Well, that means I need to break down 56. By 2 is 28. By 2 is 14. By 2 is 7. I'm looking for bundles of 3, and I got one. So I got the cube root of 2 cubed times the cube root of 7. The cube root of 2 cubed is perfect, but the cube root of 7 to the first is not. So my final answer would be 2 times the cube root of 7. Okay, 14. We're going to break down 5, 7, 6. Ends in an even, so by 2 is 2, 8. 8. By 2 again is 1, 4, 4. By 2 again is 72. By 2 again is 36. By 2 again is 18. Yeah, by 2 again is 9. By 3 is 3. And I'm looking for bundles of 3 because my index is a 3. There's 3 2's, there's 3 2's, and I only have 2 3's. So I've got the cube root of 2 cubed times the cube root of 2 cubed times 3 squared, cube root of 3 squared. Okay? Well, that's going to be a perfect 2. That's a perfect 2. And that's just going to be the cube root of 9 because there's not enough to be perfect, yeah? So 2 times 2 is 4 cube roots of 9. Alright, and 15, break it down. 162. By 2 is 81. 2 isn't going to work anymore. By 3 is 27. By 3 is 9. By 3 is 3. I'm looking for bundles of 2 because my index is a square. I got 2 3's and 2 3's. So I got the square root of 2 times the square root of 3 squared times the square root of 3 squared. And simplify the perfects. The square root of 3 squared is 3. Square root of 3 squared is 3. That has to stay in, and I get 9 square roots of 2. Alright, if we try these, we got to rationalize the denominator. I'm going to multiply by the square root of 11, but if I do it on the bottom, I got to do it on top. So on top, I'm going to have 7 square roots of 11 over 11. I can't reduce the outside numbers, so I am good. Alright, I'm going to multiply by the square root of 18 on top and on bottom. That gives me, on top, 6 square roots of 18. On bottom, it gives me 18. Well, I got to do a couple of things. I need to simplify the square root of 18. Divide by 2 is 9. By 3 is 3. So this is 6 times the square root of 2 times the square root of 3 squared over 18. Square root of 18, sorry. This is perfect. So on top, you have 18 square roots of 2 all over. And we already simplified the square root of 18, which was 2 square roots of 3. So then on the bottom, you're going to have 3 square roots of 2, I'm sorry. Because you'd have 3, again, you're breaking this down if you want. Oh no, never mind, we already multiplied, sorry, that is 18. And now those 18s cancel, and I just end up with plain old square root of 2. On 18, rationalize, so we're going to multiply by the bottom, on top and bottom. So on top I have 19 square roots of 19 over the square root of 19 squared, but that's just going to be 19. Those cancel, and I end up with the square root of 19. Alright, on 19, we have to rationalize that denominator. But what I'm going to do is I'm going to break it down first, because I don't want to multiply by another cube root of 296. You can, but that's going to be huge and a lot of reducing. So I'm going to break it down first. So 296 by 2 is 148. By 2 again is 74. by 2 again is 37. And it looks like 37 is prime. So I need bundles of 3. I got it. So this is going to be 13 over the cube root of 2 times the cube root of 37. That's just 2. So I have 13 over 2 cube roots of 37. Okay, so to rationalize this, I need to multiply by, I screwed up. If I multiply by another cube root of 37, that's just going to give me the cube root of 37 squared. I need to have the cube root of 37 cubed. So I need to multiply by the cube root of 37 squared, because that way I get 2 on the outside, cube roots of 37 cubed, which gives me on the bottom 2 times 37, which gives me on the bottom 2 times 37, 74. There's my rationalized denominator, but I have to do this up top. I'm going to do the cube root of 37 squared. So on top I'm going to have the cube root, 13 times the cube root of 37 squared, whatever that is. Okay, and over here that would cancel and you just get 37. Oh, I did that, 74. So you're going to have 13 cube roots of 37 squared on top over 74. Yeah? Alright, you tried this one. Hit pause. Come back when you're ready. And hopefully you got 1. You're multiplying like bases, so you add exponents. So we're going to have 13 to the negative 2 plus 2, which is 13 to the 0. Anything to the 0 is 1. Try this one. Hit pause. Come back when you're ready. And hopefully you got K. Alright, you could just multiply by another square root of 45. On top, that's going to give me 7 square roots of 45 over 45. But now I got to break down the square root of 45. By 5 is 9. By 3 is 3. I'm looking for bundles of 2 because that's a square root. I got that. So I have 7 times the square root of 5 times the square root of 3 squared all over 45. Well, the square root of 3 squared is 3. So I have 21 square roots of 5 all over 45. And then I can divide by 3 on these two outies. 3 goes into 21 7 times. 3 goes into 45 15 times. And I get 7 square roots of 5 over 15. Try this one. Hit pause. Come back when you're ready. And hopefully you got 1. Alright, we can't subtract exponents because the bases don't match. So you could either multiply those out and then hit divide, or just to type it in your calculator the way it is. But if you're going to do the rules, would you agree if I kept everything the same? Except for I rewrote 25 as 5 squared. I'm not breaking any laws because I still have 25 there. Now if I do Santa, I get 5 to the 4th divided by 5 to the, when you power, you multiply. 2 times 2 is 4. And anything divided by itself is 1. Okay, try this one. Hit pause, come back when you're ready. And hopefully you got 2 to the 12th. Alright, this is going to be 4 to the 7th. And on bottom, the square root of 16 is 4. That's going to be, when you divide with like bases, subtract exponents. So that's going to be 4 to the 7 minus 1, which is 4 to the 6. So how did they get that? They broke down 4. They kept everything the same, but rewrote 4 as 2 squared. And then did Santa Claus and got 2 to the 12th. Okay? Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got E. The way I did this one is I literally just, we're trying to find out which one is equal. So I typed in the square root of 72 divided by 6 to the 5th and got that. And then I typed, the reciprocal. It says all the following choices are the reciprocal of this. Well, the reciprocal of this would be it upside down. So I'd have 6 to the 5th over square root of 72, which gives me this 916. So I'm looking for all the ones that are equal to that. So I typed this one in, got it. Typed this one in, got it. Typed this one in, got it. Typed that one in, got it. Typed this one in, didn't get it, so it's E. And we are done for today. So I will see you next time for day 4.